Hi everyone, I'm Professor Adam Bergasser, and this video is going to be talking about working with vector quantities. And so the last video we talked about just working with physical quantities in general. Now we're going to focus in a little bit on a special class of physical quantities, which are vector quantities, which have magnitude and unit, and also a direction. And so some examples of this are velocity, where you want to know both the speed of an object and in which way it's moving, forces, momentum. There's all sorts of vector quantities that we're going to be talking about in this class. So the sort of overview of this lecture, we're going to be talking about how you actually write down vector quantities. That's both symbolically, graphically, and also numerically. Right? How do we actually write them down on a piece of paper? We'll also then talk about the specific vector operations. So addition and subtraction, scalar multiplication, how you stretch and shrink a vector quantity, and then also these very special operations that are particular just to vectors, and that's the dot product and the cross product, and where we use those in our Physics 1A class. So just to start off, when we write down vector quantities, you will often see a symbolic notation to differentiate these particular kinds of quantities from scalars. And so the way we'll write down vectors is we'll literally just put a little arrow above the sort of the little symbol that represents something. So in this case, this is representing the vector quantity of acceleration, and an F with an arrow over it would represent the vector quantity of force. We can also write A and F without those arrows on top, and that would just indicate just the scalar, maybe the magnitude of the acceleration or the force. But anytime you see a vector over a quantity, you should know that that's going to be a vector, and it's going to have to be treated a little bit differently. We can also represent vector quantities graphically, right? Literally draw them. And of course, if we have a magnitude and a direction, the best kind of graphical representation of that is just simply an arrow. All right, so anytime we're drawing a diagram that includes vector quantities, you'll see some kind of arrow on that diagram. Obviously, the direction is indicated by which way the arrow is pointed, but the length also has some meaning. All right, the length of this arrow gives us an idea of the magnitude of our physical quantity. Okay, so the larger the acceleration, the longer the vector you're going to see when we draw it down on the screen. Now we can also represent these vectors in a more numerical way, and of course this is the way that we're going to be able to work with them. So there's actually three ways of writing down a vector numerically. All right. The first one is to literally write down each of these pieces, the magnitude, the unit, and direction. In order to do that, we have to actually have some reference frame to point out our direction. And so we'll use a coordinate system, which I'm going to draw in pink here. All right, we'll talk about coordinate systems in a future video. But let's say my coordinate system is drawn in this direction. We have an x and y axis, and the vector has some angle phi relative to that x-axis. All right, and so I can write down then this vector quantity. So in this case, I'm going to assume that this is a vector quantity of position. We'll call it r, and the scale of this coordinate system is such that the length of this vector is equal to 5.0 meters. All right, that's the magnitude. And so it's very easy then to write down what this vector is. It's just equal to 5.0, that's the magnitude, times meters. And then we have to specify a direction. In this case, we'll specify it relative to the x-axis. This angle, as it turns out, as we'll see in a moment, is going to be about 37 degrees with respect to the x-axis. And so I could just write that down, 37 degrees counterclockwise. That's what CCW is equal to, with respect to x-axis. All right, that is specifying a direction. It's very wordy, but we have to have some way of sort of conveying which way this arrow is actually pointing. Another way we can write down this vector numerically is to actually use the coordinate system and break it down into the components that are on the different axes. And this is literally projecting our vector down onto these axes. So looking at its extension along this direction and its extension along this direction. In this case, this is going to end up being 3 meters across, and this will end up being 4 meters. The drawing is not quite to scale, but that's the way we've drawn this. All right, in that case, then we can write down this vector in terms of essentially its coordinates on this coordinate system. And so we can write that down as 3.0 meters, comma 4.0 meters, where this is the x-coordinate, we'll call it x-coord, and this is the y-coordinate. All right. So this still conveys the magnitude, at least the magnitudes along the different axes. The units are still conveyed in here, and the sort of ratio between these two values gives you an idea of the direction, at least in this coordinate system. The third way we can write this down is using something known as unit vectors. It's going to look a lot like this coordinate written form here. But instead of writing down it in this parentheses format, we're actually going to write down it as almost as an equation. It's going to be a combination of 2 vectors, 3 meters in the x-hat direction and 4 meters in the y-hat direction. Now, this is a new notation here, this hat symbol. This is indicating a unit vector, which is a vector. It conveys direction, all right, but it's always of unit length. And so the magnitude part of this is always going to be 1. In fact, we almost don't even care about the unit of it because we're just indicating a direction. So this is kind of a special vector where we only talk about direction. And so this is unit length and conveys direction. Okay. Now the last little bit to talk about here is when we talk about the length of the vector, another way that we can write that down in terms of our vector notation is we can put that vector within vertical lines. That notation conveys the length of the vector. We're trying to figure out what the magnitude of that vector is. And so in this case, this is equal to 5.0 meters. And so anytime you see this symbology here, vertical lines with a vector inside, what you're actually indicating is what is the length of that vector, which turns out to be a scalar number. It's still a physical quantity. It's got a magnitude and a unit, but you've taken out the direction part of it. So now that we know how to write down our vectors, how do we actually manipulate them? What kind of operations do we do on our vectors? So there's 4 sets. The first is just simple addition and subtraction. And a very common way that we use addition, subtraction, and vectors is looking at the net forces acting on an object. And so if I just represent some block or wheel or something like that with this box here and draw the forces that are acting on this box in the directions which they're pointing, this is called a force diagram, and we'll see a lot of these later on when we talk about applying Newton's laws. But one thing we want to know at the end here to predict the motion of that object is what is the net force? What is the sum of all these forces acting on this object? So we have a couple ways that we can do this. The first thing we can do is just do this graphically. So our first technique is going to be graphical. And the basic idea is that we just want to connect the vectors tail to head and follow their path. All right? So the amazing thing about vectors is that you can actually move them around. Their actual location in space doesn't matter as long as they're still pointing in the same direction and they have the same length. Those are the quantities that matter for vectors. And so if we want to add these vectors together, what I can do is I can literally move this vector over and add it to the head of the first vector from the tail and see where that points. And so I know in advance that this vector is about 5 inches long, and I'm going to make it point straight downward. So I'm going to put my ruler down here and just make a facsimile of our F2 vector so that it adds up to that point. So this is now adding our F2 vector. All right? Now I'm going to add in this third vector, and it's the same thing. I'm going to move the vector literally right over there. It's about 2 inches long and it's horizontal. So I'll sketch that in. All right, that was our F3 vector. And now I literally start from my starting point, follow these vectors in line until I end up with our net vector, which I'll draw in with a ruler here so I get nice and straight. So this is the sum of those vectors, all right? A short little stub that's going off in this direction, all right? So graphically, this becomes kind of just a mapping game. You move the vectors around, connect them tail to head, and then you just follow their path till you get to the last point, and starting from the origin to that last point, that gives our net vector. All right. Now, we can also do this, so this is very good if you're drawing a picture like this, but we may want to actually calculate numerically what that net vector is. And so our next step is to figure out how we do this numerically. And to do that, we're going to want to add the components of the vectors separately. Now, what do I mean by components? What I mean is the amplitude of this vector along our coordinate system axes. And so we need to draw in a coordinate system here. And so I'm going to assume that this is my origin. And we've got two directions, x hat and y hat. You can see it's getting a little bit dense of a diagram. But we can now write down our vectors within that coordinate system numerically. And we can do it in a couple different ways. So let's first write down our forces with the parentheses notation, just writing down the x and y coordinates. So for this force vector, I know that it's actually 5 inches in this direction and 5 inches in this direction. So I can write down that force as 5 newtons, with the scale of 1 inch goes to 1 newton. Now remember, force is a magnitude of the unit of force is newtons. So when I say inches, I just mean the length of the arrow that I draw on the screen here. But that's going to correspond to 5 newtons. All right? I can then write down our other forces. So in this case, the force 2 is pointing straight down. So in our coordinate system, that means it's going in the negative direction from the y-axis. And it's not going anywhere in the x-axis. And so I can write down that as 0 newtons and minus 5 newtons, because I measured this earlier to be about 5 inches, and it's 1 inch per newton. Our third vector is pointing in the negative x direction, and it's about 2 newtons in length, and there's no extension on the y-axis, and so this is going to be minus 2 newtons, comma 0 newtons. All right? So these are just writing down our forces in the numerical format, which is our coordinate format here, with these two numbers, x and y directions. At this point, adding up the vectors is just a matter of adding up each of these individual components. And so if I just start in the x, it's going to be 5 plus 0 minus 2. And so this gives me 3 newtons. All right? And here we've got 5 newtons minus 5 newtons plus 0 newtons. So that ends up to be 0 newtons. And this is our sum of our forces. Now, notice that the net vector we drew over here graphically looks to be about that value. It's in the positive x direction. There's nothing in the y direction. And if I were to measure the length of that, it'd be about 3 inches on the screen, and 1 inch is equal to 1 newton, so we got the length right. So that's one numerical way of doing it. We can also write down our vectors in our unit vector notation that I explained in the last slide. And so again, just borrowing the numbers from here, I can write this as 5 newtons in the x hat direction plus 5 newtons in the y hat direction. The second vector I can do the same, but notice that there's nothing in the x hat direction. Our F2 vector only points straight up and down, not left to right. So I'm just going to leave that blank and just write down the y hat component, all right, the y direction. So I've left this blank, but notice that I've lined this up because I'm going to look at the different components separately. And same thing here, I'm going to write down something for the x hat direction, but not write anything down in the y hat because there's nothing in the up or down direction for this third vector. And it's basically the same idea. I'm going to add up these vectors, so 5 minus 2 gives me 3 newtons in the x hat direction, and 5 newtons minus 5 newtons is 0, and so there's actually nothing in the y hat direction. And so we end up with a vector that looks like this. Again, these are exactly equivalent, and they look a lot like the drawing that we had here when we did the graphical representation. So you have kind of three different ways of combining these vectors through addition and subtraction. You can either do it graphically, or you can do it numerically using one of these two ways of writing down the vector numerically. Now I'll just say if you want to subtract a vector, subtraction is just basically flipping that vector in the opposite direction. So for example, if I wanted to do f1 minus f3, all I have to do is flip the head and tail of f3 and then follow exactly the same steps as you see here. So the second kind of operation we can do with vectors is called scalar multiplication. And this is essentially an act where we can stretch or shrink a vector by multiplying by a number which doesn't have a direction, which is a scalar. And so for example, if I have a vector a that's just pointing off here in this direction, if I multiply that by a number, all right, we'll call it a constant c just to keep it general, that's going to do one of a couple things. It may make the vector longer, all right? And when I say vector longer, that means that it has a larger magnitude, right? The magnitude part of the physical quantity has become bigger, right? That's going to be the case when we have a scalar that's greater than 1, all right? We're literally multiplying by a number bigger than 1. We could also make this vector shorter, all right? We've reduced the magnitude of our physical quantity, and that's going to happen when we have a number that's between 0 and 1 as our scalar. Right. We can also multiply it by a negative scalar quantity, and that's going to have the same effect as flipping the arrow around. As we talked about subtraction of vectors, that's flipping the arrow head to tail. So multiplying by a negative number actually does that flipping action. So that's going to end up to look something like this in the case that c is less than 0. Now in all these cases, we still have a vector that sort of points along the same general direction. It might flip directions, but it's still along the same general direction. Multiplying by a scalar doesn't change the orientation of the vector, other than possibly flipping it over if it's a negative number. Right. So let's see an example of this in the actual physics we'll be doing. One of the quantities that we're going to be talking about is momentum. And momentum is defined, right? It's usually a symbol P, and that's defined as the combination of mass times velocity. All right? Velocity is a vector quantity. Mass is just the amount of stuff, all right, that an object has. There's no direction associated with that, so that's a scalar quantity. And so combining a scalar quantity times a vector quantity ends up with a new vector quantity that's going to be scaled in some direction, but it should be in the same general direction. All right, so if we take an example of, for example, a velocity of 5.0 meters per second and a mass that's equal to 0.45 kilograms. And just for context, this is about the mass of a soccer ball, and this is about the speed or velocity of a very quickly kicked soccer ball that might go in the goal against the Japanese in the World Cup recently. We can calculate the momentum of that soccer ball by just multiplying these numbers together. All right, and so we write down our quantity 0.45 kilograms. We write down our quantity 5.0 meters per second. And I made a mistake here. I wrote down the velocity here as a magnitude and a unit, but I didn't specify a direction. And so I need to make sure I do that. So we'll call that the x-hat direction. If we're talking about, so for example, maybe on the field, all right, we have x-hat, y-hat, and here's our goal post that we're trying to shoot through. All right, we want to definitely shoot it in that direction. That's important. So we want to make sure we have a direction for our velocity. So we can include that in our multiplication here as a direction. And now we go back to our best practices for multiplying and combining physical quantities. We want to combine the numbers first, all right? And again, we'd be tempted to write down the exact number, which is about 2.25, but we only have 2 significant digits in each of these numbers. So we have to write down and round off that number in units of 2 significant digits, which is 2.3. We then combine the units, kilograms, meters, and seconds. So that's going to all combine into one composite unit, kilograms, meters per second. And now we're left with a direction quantity, but that just carries in because it's not being multiplied by anything. That's just going to stay through. So we end up with a momentum, which is 2.3 kilograms meters per second, in the same direction as our velocity. Because again, multiplying by a scalar doesn't change the direction. It may flip it, but it's still going to be in sort of the same general axis. So we've seen how we can add vectors together, and we've also seen how we can stretch them by multiplying by a scalar. You might imagine we should also be talking about how we multiply vectors together, divide vectors together. And while that works fine for scalar quantities, it's actually very hard to multiply two vector quantities together because you have to figure out what to do with those directions. It makes perfect sense to go up and to the left, but it doesn't quite make sense to go up times the left. There's really no way of conveying that. At least we'll see a couple ways that we can. So there are two vector operations that do allow vectors to be combined in a kind of multiplicative fashion. And these are the dot product and the cross product. So we'll start with the dot product. This is the notation for the dot product. It's literally a dot. And when you take two vectors and you combine them with this dot product, what you end up is a number, a scalar quantity, that tells you something about the alignment of those two vectors, how sort of in line they are, particularly in terms of their length and the direction. So to illustrate this, I've put together two vectors here. I've lined them up so they have the same tails connected to each other, and their directions are oriented so that there's an angle theta between the two of them. And here are just the representations of those vectors in our sort of coordinate system notation. So the dot product literally measures what is the projection of one vector down onto the other one. And so we can literally write that down by just taking our vector and making a perpendicular line down to our b vector. And this is the length that we're actually talking about, that projection of that vector onto the other one. Now this works both ways. I can also take my b vector here and draw a perpendicular line down to the a vector, and I'll get a length out of that. And it turns out that both of those lengths, to the limit of my accuracy of drawing, are the same. And so our quantity a dot b is just equal to these lengths that are projected onto each other's axes. So we can write that down in more mathematical notation. There's two ways of actually calculating numerically what the dot product is. First, we can calculate it as a combination, a multiplicative combination of the lengths of those vectors, the magnitudes of those vectors, times the cosine of the angle between them. Right? Now remember this notation. This is a measure of the length of the vector, and since the length is a positive number, and generally these two numbers are going to be positive, and whether this number, this combined dot product, is positive or negative will depend on what the angle is between them. Another way we can write this down is by combining the coordinates. And so the dot product also looks component by component and multiplies those components together. And so another way of writing this quantity is to actually write down the sum of the products of the components. All right, so in this case, xa times xb plus ya plus yb. Both of these expressions are equivalent in terms of computing the dot product, and which one you use will depend entirely on sort of what kind of quantities that you know. Now, I'll just do a couple quick notes about sort of the general properties of dot product, and then we'll run through an example next. Sometimes we'll have examples where these vectors are the way I've lined it up before, where they're generally pointed in the same direction, but they're separated by some angle. So let's take an example. Let's say theta is equal to 30 degrees. All right? In that case, they're separated, but they're still kind of pointing in the same direction. Cosine of 30 turns out to be 0.87. And so that means that our dot product a dot b, which is the length of A, length of B, times 0.87, all of these numbers are positive. And so that means that the dot product is going to be greater than 0 when the two vectors are generally lined in somewhat the same direction. The opposite case is, let's say we have the two vectors that are separated by a much wider angle, so that they in general point in slightly opposite directions. And so this angle theta might be, for example, 120 degrees. Well, the cosine of 120 degrees is equal to minus 0.5. And so a dot b is again equal to the lengths of those vectors times minus 0.5, this is always going to be less than 0 because, again, these lengths are always positive. So if two vectors point generally in the same direction, you get a positive dot product. If they point in slightly opposite directions, you're going to get a negative dot product. The third possibility is that you have vectors that are exactly perpendicular from each other. In that case, theta is equal to 90 degrees, so that's a right triangle, a right angle. And cosine of 90 degrees turns out to be 0. And so in the case where two vectors are perpendicular, their dot product, magnitude A, magnitude B, times 0 is always going to be 0 if A is perpendicular to B. So in addition to providing a way of kind of multiplying or combining these vectors together, the dot product provides a way of determining if two vectors are perpendicular, parallel, or anti-parallel, and the degree of parallel and anti-parallel they are. And so that's one of the reasons the dot product is so useful. So as an example of how the dot product is used in physics, it's commonly used for calculating the work done by a force applied to an object. All right, this is part of our work energy theory. Work is the change of energy of an object. And so if I wanted to, for example, calculate if I'm pushing a box across the ground and I'm kind of pushing at it at an angle, if I wanted to compute the work done on that box by me pushing on it, I actually have to consider the orientation of the vectors of the force applied and the displacement of the box as it moves. And so let's approach this as our sort of normal way of solving physics problems. I've got a figure here where I've drawn both the force vector and also the displacement vector, and I've got my coordinate system so I keep track, and then here's my angle, which is about 30 degrees as I'm pushing it down. And so again, what we want to write down first is what do we know? And in this case, we want to write down the quantities that we know in their vector format. And so we have our force vector, which has an amplitude of 10 newtons, a magnitude of 10 newtons, sorry, a magnitude of 10, a unit of newtons. And we can write down the direction as 30 degrees below horizontal as sort of our wordy way of writing a direction. Or we can write this force vector in its components in our xy coordinate system. And so I will just write those down. I'll leave that as an exercise to actually figure out why they are written in this way. Right? So we'll just make sure we stick in our units here because they have to be in there. Right? So, and of course this is a minus 5 newtons. So we have 8.7 newtons going off to this direction, the positive x direction, and we have 5 newtons in the negative y direction. So this is our force vector in its components. The displacement vector, delta r, is equal to 4.0 meters, and this is entirely along our x-hat direction. So this is writing it down in our unit vector notation. Again, I can write this down in our coordinate system. It's all in the x-axis, so it's 4.0 meters and 0.0 meters. All right, so what are we actually trying to solve? What are our relevant equations? Well, as we will see later on in the quarter, to compute the work, what you want to calculate is the force dot displacement. All right, so here's a perfect example of our dot product. So let's try to calculate this from our two different methods, one using the amplitudes and the angles between the vectors, and one using the components. All right. So in the first case, the amplitude of our force vector is simply 10 newtons. All right. The amplitude of our displacement vector is 4.0 meters. And then we multiply this by the cosine of the angle between them. So in this case, that's 30 degrees, so it's cosine of 30 degrees. And when you solve this all out, you're going to get 35 Newton meters. Now, I've already rounded down to the significant digits of our values, which are 2, both for 10 newtons and 4.0. Cosine 30 degrees is about 0.87, but of course you can write down lots of digits after that. But if we round everything out, it's about 35 Newton meters. Newton meters as a unit is also equivalent to 35 joules, which is our unit of energy. All right, so that's one way of calculating this force vector, or sorry, this work quantity. We can also calculate by multiplying the components of the force and displacement vectors together. All right, so that's taking the x coordinates multiplying those together, plus the y coordinates, and so this is going to be 8.7 newtons times 4.0 meters plus minus 5.0 newtons times 0.0 meters. And of course, this side of it's going to go away. And so we're left with exactly the same result. This is going to be 35 Newton meters or 35 joules. Okay, so both of these ways of calculating the dot product are useful depending on what kind of information you have. If you know the amplitudes and the angle between the vectors, it's very easy to use this, this formulation, the magnitude of the vectors and the angle between them. If you know the components of your vectors, then it's very easy to use this component form. Either way is correct, and they both give the same answer. Our next multiply-like operation for vectors is called the cross product, and this is something that measures the perpendicularity or the rotation of one vector into another one. And that term rotation should give an indication that we're going to use this particularly when we get to the end of the quarter when we talk about rotational quantities like torque or angular momentum, which are all calculated using the cross product. Unlike the dot product, the cross product actually produces a new vector whose direction is actually pretty interesting, as we'll see in just a moment. And so again, let me take two vectors, A and B. We can calculate the value of the cross product in much the same way as a dot product, where we've got the magnitude of the two vectors, or their lengths, and this time times the sine of the angle between them. And so if this is the angle between vector A and B, it's the sine of that angle that we want. Now, I mentioned that the cross product produces a direction, so we were actually not quite finished. This is a magnitude. We now have to indicate a direction, and I'm going to just symbolically represent that this direction that comes out is perpendicular to both A and B. Now, how in the world do we get a vector that's perpendicular to both of these vectors? Well, we can't do it on a screen like this. We actually have to jump out into the third dimension. And so the way we actually calculate that direction is using the right-hand rule. All right. So the right-hand rule is pretty easy. You take your right hand, you point your fingers in the direction of the first vector, which in this case is A. You wrap your fingers in the direction of the second vector, which is B. So I'm going from A wrapping to B. And then my thumb is going to point in the direction of the cross product result. In this case, that thumb is pointing into the board. And so in order to write down that vector, A cross B, I have to write a direction that specifies into the board. And we actually have a symbol for that. It's this little cross or X with a circle around it. That is indicating into the board. And you can think about it almost as like an arrow that's flying away from you into the board. You're looking at the back end at the feathers of the back of the arrow. That's kind of that symbol. The opposite symbol, so let's write that down. So into the board is equal to this cross symbol. And then out of the board, or toward you, is a dot with a circle around it. And that's kind of the point of the arrow coming at you. Okay, so we have these new unit vectors to kind of display directions that are kind of putting us into another dimension away from the glass here. All right, so that would be the case of A cross B. All right, that's pointing into the board. We can also do the opposite interaction and look at what B cross A. So let's do the same right-hand rule. My fingers point toward A. My fingers then wrap around into the direction of A. And notice now that my thumb is pointing at you, all right, out of the board. And so we actually have the opposite direction. And so if A cross B is the magnitude of A, the magnitude of B, sine theta, and then out of the board, or sorry, into the board, B cross A is magnitude of A, magnitude of B, sine theta into the board in the opposite direction. So the take-home point for this is that for the cross product, the order of the vectors matters. And if you think about it in terms of the cross product measuring something like rotation, it does make a difference if we're rotating from B to A versus A to B. That's a different motion. It's the reverse rotation. And so having some directionality to this product, this particular operation, is important in that sense. One last thing I'll point out about the cross product is that, of course, it depends on sine theta. So if we have the case where A and B are aligned, so the angle between them is 0, sine of 0 is 0. So cross products disappear when you have two vectors that are co-aligned, either in exactly the same direction or 180 degrees. In that case, you also have sine of 180 degrees is 0. You have 0 as the cross product. So while dot product disappears for two perpendicular vectors, the cross product disappears for two vectors that are either aligned or anti-aligned. So we've talked about all sorts of properties of vector quantities, which you're going to be using in this class. Here's just a summary of some of the things we've talked about. First of all, just the definition of what a vector quantity is. It's a physical quantity that has the magnitude and unit that a normal physical quantity has, but it also has direction. And that's very useful for some physical quantities where direction is important, like the velocity of an object or the force being applied. We have different ways of representing vectors. Symbolically, it's just adding a little arrow on top of our symbol of whatever quantity we're talking about. So for example, for acceleration, it might be an A with an arrow over it. We can also represent vectors graphically, literally with arrows, where the direction of arrows gives us the direction of the quantity, but the length of the arrow actually tells us something about the magnitude of that quantity. So here, for example, I have an A arrow where I've drawn it with some length that corresponds to 5 meters per second squared. We also have numerical representations for vectors where we can break it down in terms of the coordinates of our coordinate system. And so that might be in this sort of parentheses notation, or it may be represented using unit vectors that you're multiplying the coordinates by the individual unit vector. We've also talked about all sorts of operations for vectors. Adding and subtracting vectors is following tail to head and following the path along. So if you have A and B, the resulting vector is just the sum of those two vectors added together. And we can also compute that numerically by just adding up the components separately. Now, one thing I'll point out that I forgot to point out before is that we can add vectors together, but we can't add scalars to vectors because it doesn't make any sense to add something that has no direction to something that does have a direction. They're very different kinds of quantities. So we can add scalars, we can add vectors, but we can't add scalars to vectors. However, we can multiply a vector by a scalar. So scalar multiplication or scalar division are both reasonable operations to do. And that simply takes our vector and stretches or shrinks it depending on the value of that scalar constant, or may even flip it around if that constant is negative. And so you can actually compute that, again, in terms of components by just doing essentially distributed math. You're multiplying that constant times each of the components within the vector. That will stretch it or shrink it or flip it around. We have two operations that are very similar to multiplication for vectors. One, the dot product measures essentially the alignment of two vectors with respect to each other. It produces a scalar quantity that measures that alignment, and that can be computed either as the product of the magnitudes of the two vectors times the cosine of the angle between them, or you can compute it using the individual components, multiplying those components together. So multiplying all the x components and adding that to all the y components, and if you have z other axes, you can do that as well. And our final operation is a cross product, which we're going to see in rotation, and that's actually measuring the either perpendicularity of two vectors or how one vector rotates into another one. And we've been able to calculate that rotation using the right-hand rule. And so taking two vectors like A and B, we can compute that the direction of A and B is indicated by our thumb with the right-hand rule, in this case pointing into the board. And we can also compute the magnitude of the cross product, again by the product of the magnitudes of the A and B vectors, in this case times the sine of the angle between them, sine of theta. And again, that produces a vector quantity that points in a certain direction. and that direction will depend on the order in which you're cross-producting these vectors. So we'll see these operations as we go through the course. Adding and subtracting is going to be very important for adding forces together to find the net force acting on an object. Scalar multiplication defines many of our physical quantities like momentum. The dot product is going to be very useful when we talk about work and energy. And the cross product, because it measures rotation of one vector into another one, of course is going to be very useful for our rotational quantities like angular momentum and torque.